So I have discussed these three bifurcations: saddle node, transcritical, and pitchfork. And there were few questions. I said that I'm mostly interested in the supercritical form, and there were few questions that what is the difference between subcritical and supercritical. So I will start from there, and then I will move to this Hopf bifurcation. Okay. So just let me consider just this pitchfork one. I said that it is ax minus x cube, right? So in this form, I found that the bifurcation diagram that I got, it was stable one, this is unstable one, and then there is this is x. Fine. So what you see that as you vary A, there is a change in stability, right? So the equilibrium point, it is changing its nature with variations in A basically, right? Because the eigenvalue that we have calculated, that's a function of A, right? So here this A is actually a driver. You slowly drive it, right? So the point of how fast we are driving a driver, that will come at some point. Here we are just gradually changing it. Okay. So the point is that what we will do in a numerical simulation, I have this equation, I'll fix one A value, simulate the system, remove the transient, and simply see where the system is, right? So you can think of, let's say, I fix that A value at -1, fine, and I know that x equals to 0 is the equilibrium point, fine, and that's the stable one. So if you start from any initial condition, then it may eventually take some time and then settle, right? So you see that here, for a particular A, this x equals to 0 settles into this, a trajectory settles into x equals to 0, right? And this is time and this is x. So what I have drawn here, simply a time series. Right? So this is a transient time. This is transients. So the time the system needs to settle into the potential well. And here, after the system reach the steady state, it will be there, right? So now, when I have such a situation, then if I consider, now this is for A -1, this is the situation. So until I reach up to A0, then eventually I will always settle into that x equals to 0, right? Now when, let's say I consider A equals to +1, right? Now then I have two steady states, right? So they are x equals to plus root over A and x equals to minus root over A, and in between there is this unstable one, fine. So now you see this unstable one, so this is my so this is, let's say, with time, and this is x, right? So now if I take one initial condition here, system cannot converge to that equilibrium point, right? So it has to, it will take me some time, it will converge to that equilibrium point. And if I'm below, then it will converge to that equilibrium point, right? At one time, if there is, you cannot be at both the equilibrium points. Can you be both the equilibrium points? No, right? Because it's a deterministic one, and you cannot cross the potential well. And can you be at the unstable one at x equals to 0? Yes, you can be at the unstable one only when you start at x equals to 0. So the point is that here, depending upon the initial condition, you will be either at the upper branch or at the lower branch. You cannot, one object cannot stay in two places at a time, right? But earlier, with the variation for negative, with the variation of A, it was always there. So initial condition was not playing a role, right? So the equilibrium point was globally stable. Someone has asked me, so the equilibrium point was globally stable, right? Because there was no alternative attractor. So anywhere in any initial condition, so the notion of basin of attraction will come. Anywhere from the phase space you start, you will converge to the equilibrium point. So it was a globally stable equilibrium point, right? But here it is not the case. Here they are locally stable, right? If you start only in the basin, then you converge there to that particular equilibrium point. Otherwise, you cannot, right? So now this one is an example of supercritical pitchfork. Now we can also talk about one which is subcritical. So that is x dot equals to ax plus x cube, right? Can you calculate the bifurcation diagram, all of you? Please calculate the bifurcation diagram. It's very simple. So we have x equals to a plus x square, right? And f prime x, if I say x dot equals to fx, then f prime x is a plus 3 x square, right? So now the equilibrium points are if x equals to 0 will result in x equals to 0 and x equals to plus minus root over minus a, right? Plus minus root over minus a. So this will only exist when a is yes. So there is no oscillation. Yeah, there is no oscillation. If you fine with that. So in the subcritical one, so here it is. So this fixed point will exist when a is less than 0, right? So now can you calculate the bifurcation diagram? So at f prime 0, it is coming out to be a, right? And at f prime plus minus root over minus a, it is coming out to be a minus of 3a. So that is minus of 2 I say, right? So this one is stable when a is less than 0, and it is unstable when a is greater than 0. So that's a, and this is x, right? And these two they will exist when a negative, right? But if a is negative, then minus of 2a is greater than 0. So this is greater than 0 when a is less than 0. Fine. So diagram is like this. Fine. Anyone is having any question? Fine. So now the point is that why we were always interested. I said that I am mostly interested in. So the subcritical and supercritical concept will come when I talk about Hopf and Pitchfork. Okay. And so why I was interested in the supercritical one, because here you see there is, if you gradually move this parameter A, you can come from this stable one to this side, but there is no alternate. There is no alternate attractor, right? The system will not shift to an alternate attractor. Fine. So that's why I am mostly interested in the supercritical one, because here, if I cross from this side, I'll either settle into this or settle into this one. Fine. So there I have, if I gradually vary my A, after I cross the bifurcation point, I have an attractor. But there, if I vary it, I do not have an attractor. Right? So that's why I want to confine myself mostly in supercritical one. Fine. So now let me discuss Hopf bifurcations. So Hopf bifurcation cannot happen in one-dimensional system, because it needs that the system to oscillate. Okay. So and for oscillation, if we just simply start with this very simple equation, x double dot plus x equals to 0. Right? So though I have not established this theory, from here also you can perform linear stability analysis. Okay. I can write it like x dot equals to y, and then y dot equals to minus of x. Right? This I can think of f of xy, and this I can think of g of xy. I could uncouple the system, right? Then I can perform the similar linear stability analysis. So I can consider f of xy, f of x star y star equals to 0, and g of x star y star equals to 0. That will give me my equilibrium point x star y star, or you can say this fixed point. Fine. And then you can perform the similar analysis. I will not do that. So you have this equilibrium point x star y star. You partner with, let's say, eta and gamma. You push them at x, y. You write the perturbation, evolution of the perturbation, and then what you eventually get, you get a linearized system. Let's say some delta dot equals to J delta. I will not talk about it because I will mostly keep myself in the framework of Saddle-Knot bifurcation, widely studied critical transition. And this J is called the Jacobian. This is called the Jacobian matrix, and this Jacobian matrix, a little bit of calculation can result. Del f by del x, del f by del y, del g by del x, and del g by del y. Right? So, and then what one has to do, one has to calculate these values at the equilibrium point x star y star. This will result two eigenvalues. Lambda equals to A plus minus IB. So this A can be sometimes 0. You get purely complex imaginary eigenvalues. The B can be 0. You can get purely real eigenvalues, right? And you can then you can also have complex conjugates, right? So these are the possibilities. Fine. And so to have in Hopf bifurcations, there the idea of oscillation will come. Right? The idea of oscillation will come. So if we simply solve this differential equation x double dot x plus x equals to 0, we are going to get x equals to a cos t plus b 90, right? Right? Because auxiliary equation will be m square plus 1 equals to 0. You can consider a trial solution e to the power x e to the power mt, and then from there you can just get the auxiliary equation, right? And that would come m square plus 1 equals to 0. That will result m equals to plus minus I, right? And the basic differential equation solution says that x will be a cos t plus b sin t, right? So here, if I want to draw the time series, I'll be getting our oscillatory time series. Fine. But the point is that here, so if I want to draw them in the xy plane, right, what I am supposed to see? I am supposed to see a closed invariant curve. Why I am telling it is invariant? Because if you start on this, you will always stay there, right? Now the question is that if you start from this point, or if you may start from this point, what are you going to get in this equation? You are going to get another closed invariant curve, right? Because here you see no e to the power term is involved, right? So these are purely imaginary eigenvalues. Okay, so here if you start, you are going to get another closed invariant curve. If I start from here, I am going to get another closed invariant curve, right? So I change my initial condition and I am going to get closed invariant curves, right? So these are called isolated, these are called non-isolated closed invariant curve. Why I say non-isolated? Because nearby curves are also closed, right? And this is the notion of center. This leads to the notion of centers, and they are neutrally stable. Means that if you perturb it, you are again going to get a closed invariant curve, right? There is no question of coming back to that point or not. Fine. So now I have introduced the notion of oscillation, right? And it is very clear that to introduce the notion of oscillation, you need to have minimum 2 dimensions, right? And what we got in terms of oscillation, that is center, and that is an isolated closed invariant curve, non-isolated closed invariant curve. Now just let us consider this system mu x plus y minus x square plus y square, and y dot equals to minus of x plus mu of y minus of y x square plus y square.
Can I ask a quick
Yes.
question? Just
Yes.
Is there some way to motivate these set of equations?
From some real system?
Yeah, some physical intuition, if possible, you know,
I
because
don't
there are so many
remember.
new terms that are suddenly added now. It might help everyone to, if possible, but we can always.
I don't
ignore.
remember at this moment.
No problem. Thanks.
But eventually my target is to take this equation to that normal form, right? This is the simplest possible one. I said that the normal form would be r dot equals to, in this case, it would be mu r minus r cube and theta dot equals to -1. Right? And this equation I want to take there. Fine. So, but as I said, we are here. I am having two variables, right? The motion earlier, the motion was always on a line, right? And here the motion is on the phase plane, right? Because it's on the xy plane. Because I have introduced the notion of oscillation. So now to convert this into this polar form, what we can do, just consider x equals to r cos theta and y equals to r sin theta, right? So then you know x square plus y square equals to r square. I can take derivative. I'm going to get r dot equals to x dot plus y dot. So that will give me r dot, this x dot equation I'll put from there, mu x plus y minus x into x square plus y square plus y dot is minus x plus mu y minus y x square plus y square, right? We can do a bit of simplification. Then we are going to get mu x square plus y square, then xy and xy, that is going to get cancelled out. We have minus of x square plus y square into x square plus y square, right? So that implies r dot x square plus y square is r square. So mu r square minus r to the power 4. So that results r dot equals to mu r minus r cube. Fine. And then from there we can get tan of theta equals to y by x. So then theta is tan inverse y by x. We can again take derivative. So theta dot is 1 by 1 plus y square by x square, then x square y dot x minus x dot y. Fine. I hope I'm not making a mistake. Fine. And then from there we can get theta dot equals to 1 by x square plus y square, then x, this y dot value we will get from there, that is minus x plus mu y minus x plus mu y minus of y x square plus y square minus of y into this x dot is mu x plus y minus of x square plus y square. So that would give me 1 by x square plus y square minus of x square mu xy and minus mu xy will get cancelled out, and xy minus xy x square plus y square and plus xy x square plus y square will get cancelled out, and in that side I am going to get minus of y square. So it is minus of x square plus y square by x square plus y square is minus 1, right? So I am at this equation r dot equals to mu r minus r cube and theta dot equals to minus 1. So I have both the radial as well as equations for radial as well as the angular motion, right? So theta dot negative means, so theta is decreasing then, right? So theta dot equals to minus 1 represents clockwise motion. Fine. Now I have r dot equals to mu r minus r cube, right? Obviously you see that r equals to 0 is coming out to be one fixed point, right? So in the vicinity of r0, in the when r is approximately equals to 0, then that results these higher order terms we can exclude, right? I have r dot equals to mu r, right? So it is very clear that r equals to 0 is stable when mu is less than 0 and r equals to 0 is unstable when mu greater than 0, right? From there I can also get r dot equals to r mu minus r square, right? So you are getting also r equals to root over mu as a fixed point. I will not consider the negative one, right? Because it is the radius. So r equals to root mu is a fixed point here, right? So it gives you a circle with radius root over mu, fine. And so now you see if r is less than root mu, if r is less than root mu, then what is happening? If r is less than root over mu, then this r dot is greater than 0, because you see if r is less than root mu means r square is less than mu, right? So this term is positive, so r dot is greater than 0, right? So it will spiral then, spiral outward, and if r is greater than root mu, then r dot is less than 0, so the radial length is shrinking then, right? So it will be spiral inward, right? So what we have, that if mu less than 0 and I want to think about this xy, right? If mu less than 0, then obviously this r equals to root mu does not exist, right? because it's the radius. It has to be a quantity with positive magnitude. So what would happen there? So this one is basically an spiral attractor, and the motion will be, so if you take any point here, it will be spiraling towards it in a clockwise motion, right? Clockwise motion comes from the idea that this theta dot is negative, right? And now if mu is greater than 0, what we got? We already got a closed invariant curve, right? That is r equals to root mu. And the closed invariant curve, obviously, this motion will be in the clockwise direction. It is invariant curve because if you take any point on it, it will stay here forever, right? Now, as I said, if r is less than root mu, then r dot will be greater than 0. So it will be spiraling outward. So if I take one point here, it will basically try to converge to that closed invariant curve, right? And if r is greater than root mu, then r dot is less than 0, it will spiral inward. So they would be all try to come like this, right? And this is the closed invariant curve. Any confusion? Anyone is having any confusion? Fine. So here you see that when mu is less than 0, I have only one equilibrium point, that is r equals to 0, and that is a spiral attractor. But when mu is greater than 0, I have there, this one is already there, but that's an unstable equilibrium point, right? And if I take, so the point is that if I perturb from the closed invariant curve, then what would happen? It will eventually again go back there, because these spirals are going outward, and here if I perturb from here to, if I perturb one, it will eventually come back here because it is trying to shrink its radial length, right? So in that way, what you get a stable closed invariant curve, and this closed invariant curve is called a limit cycle, right? This is isolated or it's non-isolated? It is isolated, right? So this one is, so what we have, this is an isolated closed invariant curve. This is an isolated closed invariant curve because no nearby trajectories are closed, right? No nearby trajectories are closed. So now if we want to draw a bifurcation diagram, obviously I'd like to vary the parameter mu. So this one is the stable one, right? R0 means obviously I can draw it in the xy plane, right? R0 means x and y, both of them are 0. So this is x. Now this one becomes unstable as mu becomes positive. So this is stable, this one is unstable, and you are gradually changing your mu. Here what you get, this one is basically the, if you at this point, if I draw the time series, that is the upper and lower amplitude, right? If I take any point here, it will basically converge to that point, and here also they are spiraling inward. So what has happened here? If I draw a time series Ex, then eventually it will go and come settle here, right? There, if I draw a time series, I may take one initial condition like this, but after some point you will get a stable oscillation. This is transient, this is t, this is x. Let's say you plot it at mu equals to right? So here as well, when you cross the, if I want to calculate the eigenvalues, I have to use the idea of Jacobian matrix. Okay, so I have to use the idea of Jacobian matrix, and the eigenvalues, I actually didn't wanted to tell much about it, but still. So here one thing is very clear: x equals to 0 equals to y, that is the fixed point, right? If you solve it, you're only going to get x equals to 0 equals to y, right? And then the Jacobian would be del f del x. So it is fx, fy, gx, gy. This Jacobian comes from linear stability analysis. If you want to know more, I can talk about it. So there, this Jacobian matrix will come out to be mu 1 minus 1 and mu, right? Because all the other components, they will use either x or y, and we have to evaluate it at the point 0, 0, right? So eventually you are only going to get this, and then one can calculate the eigenvalues of this square matrix. So you have to solve j minus lambda I equals to 0. That lambda is called an eigenvalue, right? Which will, in the 1D case, it was just a prime x. So if you just so that would come lambda square minus trace of a into lambda plus determinant a, and this lambda will come mu plus minus I. Fine. If you solve that quadratic equation, the lambda will come mu plus minus I. So as you vary, as you play with your mu, the equilibrium point will change its nature from a spiral attractor to eventually that will become a spiral repeller, but it will also give birth to a closed invariant curve, right? Now those who work on this tipping point literature, you know that, like, if we are at this stage, right, then we have one steady state trajectory, right? It may be fluctuating, and we can use that part to forecast whether a critical transition is going to happen or not. Now I pose this question: if you are at the other side, right? If you are at the oscillatory part, can that early warning signal will still work, right? So that's a question. Those who work on, right, non-equilibrium systems, so they can think about it, right? So most literature exists, like we have a time series, so that time series is steady. We plug it in some machine that is called early warning signal, and we get some indicator. I will come and talk detail on it. So then here comes this question that if I at this in the left side, it's fine, but here on the right side, and the WS will still work. I'll come to that question. Fine. So this, now I have talked about all these 4 classes of 4-dimension 1 bifurcation, right? So, and the first one, saddle node, will give birth to catastrophic transition, or a catastrophic transition will include the saddle node bifurcation, because there is a possibility of sudden jump, and the non-catastrophic one are these 3 bifurcation: transcritical, pitchfork, and Hopf. There is a fantastic paper by Carl Boettiger. So he is a faculty of UC Berkeley. So you can take a look at this paper. The title of the paper is Charted and Uncharted Territories of Critical Transitions. It talks about all the possible kind of critical transitions that can happen, and that paper also, it's a paper published in probably Theoretical Ecology. So Alan Hastings is the editor of the journal. So he talks about, like, majority of the work that people have done until now, that is on this catastrophic part, But in the non-catastrophic one, there is also critical slowing down will also be there, because a system, to change the stability, the system has to cross this equilibrium point, but eventually, so lambda has to change its sign. So the early warning signals that will come at a point that will also work, but this non-catastrophic one, people have studied really less. So now the one I have talked about, they are in the framework of smooth dynamical system, right? So by smooth dynamical systems, I just want to talk a very little bit about it, but later we can discuss more on this. So here what has happened, like to change the stability, eigenvalue has to cross this 0 point, right? Eigenvalue has to cross this 0 point. Now, can you think of a bifurcation? Eigenvalue here lambda is less than 0 and here lambda is greater than 0. So if you move from here to here, in a smooth bifurcation framework, you will smoothly cross 0, right? Now let's say such a situation arises where you jump from a negative to a positive. Getting my point? If your eigenvalue can jump from a negative one to a positive one, then it is not crossing that lambda equals to 0, right? Still a critical transition can happen, right? Because there is a change in the stability of the equilibrium point. But what will not be there in such a system? Can anyone tell? Critical slowing down will not be there, right? There will be no CSD, right? There will be no CSD because it is not crossing lambda equals to 0. And such cases are fundamentally unpredictable by using these early warning signals, right? So the framework that we will be mostly using are in the framework of smooth dynamical system, where we are assuming that when a change of stability happens, it has to smoothly cross that lambda equals to 0. Okay, there exists system where such a situation can arise. The non-smooth one, we are not going to consider. Okay. Now let me give you one example. Okay, so this is a model of insect outbreak. Here, this is a logistic growth function, and this is a Holing type 3 response. Fine. So this is, you can think that as a growth term, and this is a death term, right? So this growth minus death will result mass balance, and if you want to think from the point of view of per capita growth, so this is 1 by n dn by dt equals to r 1 minus n by k minus bn by this is b, this square is b, n by s square plus n square. Fine. So this is the equation where this is a logistic term and this is a functional response. So this is a growth term and this is a death term, and that it can result really interesting dynamics. Okay, I'll talk about it. So if you apply some non-dimensionalization, I will not do the detailed calculation, you will get a system like this: Rx 1 minus x by k small k minus x square by 1 plus x square, right? Can you do an equilibrium point analysis? So here your fx is fine. So one equilibrium point we immediately get, that is x equals to 0, right? And the other equilibrium point, you have to solve that. Is eventually coming cubic equation, right? Can you solve that? If you cannot solve it, then how we can talk about the stability of the equilibrium points that will come from that nonlinear part. So we get an equilibrium point x star equals to 0, and the solution of this equation are 1 minus x star by k minus x star by 1 plus x star square equals to 0, right? So what will be the stability of this equilibrium point x star equals to 0? Because you see all the other terms, if you just calculate a prime x at 0, what would that be? A prime x when x star equals to 0, what that value will be? Yes, that will be r, right? Because all the other terms, they will include x. And this is a population model, and where this r is the growth rate, right? So it will be positive. So this equilibrium point, so this is greater than 0. So x star equals to 0 is always unstable, right? Now to find solution from this equation can be a bit tricky, right? But if we consider these two as two functions of x star, let's say I consider that is f of x star, and this the other one is g of x star equals to 0, where f of x star equals to r into 1 minus x star by k, and g of x star equals to x star by 1 plus x star square. Then graphically you can talk about the equilibrium point, right? So those equilibrium point will be intersection points of these two functions, right? So this one will result just simply x equals to k. So I have x, and along this I draw these functions, right? F comma g. So now at x0, this function is coming out to be r, right? And at xk, this function is coming out to be 0. So it is here k, and here it is r, right? And this function, if you draw, it will come like this. X by 1 plus x square. Right? So here you get one fixed point already. Right? So then that fixed point will be on this line. Right or wrong? That is on this line. Right? Because that will give me that x value. That will give me that x value. For that x value, these two curves, they intersect. Right? Now, can you tell me the direction of the arrow? Whether it's a stable equilibrium point or it is an unstable equilibrium point. So you just have to see that whether x dot is greater than 0 or less than 0, right? So this function is fx and this is gx, and I am calculating fx minus gx. So when fx is greater than, so this curve gx is below and this fx is above, so fx minus gx will be positive, so motion will be towards right. Similarly here, this gx is more than fx, so x dot will be less than 0, motion will be in that direction, right? Now you see that you can play with, you cannot play with x plus 1 by x square, right? There is no parameter involved. But I can obviously play with these parameters r and k, right? So if I play with that parameter, let's say k, here I have the function and this one will not change its shape, and if I can play with my k, I can have such a situation, right? So this is now my k. So my equilibrium points are, one is here, another one is here, and another one is there, right? So here, this is my gx and this is fx. Now fx is more than gx here, so motion will be towards its right. Similarly, it is towards left. Here, gx is less than fx. And here, similarly, this. So what you get these two fixed points as stable and this one as unstable, right? So with variations in k, I can reach. So this x star equals to 0 is always unstable, right? And I can play with my k to change the stability the way I have shown here. Any question? Fine. So there, now what I can do, and similarly you can also play with your r, right? Similarly you can also play with your r. If I fix my k, right, I can then take my r up, right? And also I can put my r down. If I take my r up, yeah, there, what will happen? A saddle node bifurcation will occur, right? Because you see, from two here, this one is stable and this is unstable. If you play with your r, this line will be like that, right? So these two equilibrium points, the more r I increase these two equilibrium points, what will happen? They will come closer, right? They'll come closer or not? They'll come closer, and then they will disappear. So at that point, there will be a saddle node bifurcation, right? So it is possible to calculate those bifurcation curves, right? How to calculate those bifurcation curve? One thing is that these fixed points we can calculate by just taking fx equals to gx. Let's say this is condition 1, right? And at a bifurcation point, what would happen? Their slope must be equal, right? The slope must be equal, they have to be tangential to each other. So that will result f prime x equals to g prime x. Now, when you solve these two equations together, you get some functions k as function of r. Here, such an explicit form is not possible, so we will do it numerically. Okay? Any question up to that, please? Those who are not very familiar with nonlinear dynamics may not be that simple. Any question from these two figures? One thing is very clear, that fx equals to gx is going to give me a bunch of equilibrium points. They are solutions, right? And I cannot play with gx because gx is x by 1 plus x square. There is no parameter involved, right? But obviously, I can, in the model, I can play with the growth rate. I can also play with the carrying capacity, right? So then I can play with that, this line, right? And the position of this line will determine the equilibrium point is stable or unstable, right? That idea from where we got? Because that idea already got from the very first example that I have started with, x dot equals to sine of x. If x dot is greater than 0, then the motion will be towards right, and if x dot is less than 0, motion will be towards left, right? So here, it's clear, I guess, to all of you. Fine. So now you see that if I want to draw from there, what I will get some curves. Okay, those are called bifurcation curves. Fine. So I will get such a shape. In this zone, this is bistable. And this is a monostable zone. Right? So if I fix this k value here, right? So what will happen? If you choose a combination of r and k here, how many fixed points you are going to get? Only one, right? And so here, if you choose a point here, you are going to get one fixed point. If you choose a point here, how many fixed points you are going to get? No, not 2, 3. You are going to get 3 fixed points, right? This one fixed point will be obviously stable, right? And these 3 fixed points, 2 will be stable and 1 is unstable. So this is the condition for which we have such a situation, right? So here, out of these 3 fixed points, 2 stable and 1 unstable, right? So if I want to draw, if I fix that k value there, let's say I fix this k value at k1 and I also choose 1 here at k2. Okay, so if I choose a k value, k equals to k1, and I want to plot the abundance x with respect to a variation in r. right? I am varying my R and I have fixed my K equals to K1, right? So I am basically in a monostable zone, right? So if I increase my R, then what would happen? There will be a change in a growth rate, right? So here, if I decrease my R, so then what would happen? I can see, so if I'm declining R in that direction, I can see such a diagram, right? With decrease in R, X is decreasing. Fine. Now, if I fix that K equals to K2 and again draw a diagram with respect to R, what I'm going to get so if I now want to plot it, let's say this is decreasing R, then what would happen? I will get something like this, right? The abundance is declining, right? Then I have the bistable zone, right? So it will first experience this line. This is none other than a saddle node bifurcation, because I will get this from these equations. And this point will also be a saddle node 1, right? And you see there is an intermediate region. If you are above this, how many fixed point you have? 1. If you are below it, you have 1. Intermediate, you have 3. You are going to get such a diagram, right? So this is when you are above that line, you are below that line, and intermediate, you have both stable fixed points, and in between there will be this unstable, right? So I stop here. In the next class, I will elaborate this in more detail. Any question, please? Obviously, I did not do, for the Hopf bifurcation case, I did not do that linear stability analysis in detail, but it will simply follow the way we have done for 1D system. You have, instead of just the motion will not be on a line, it will be on a phase space, and you need to introduce the concept of Jacobian and eigenvalues. So here I am, what I am doing here, I am decreasing R, right? So then the abundance is no, here I am considering it that I am decreasing R. I've just converted the position. That is your choice, right? But it is quite natural to think that if you decline R, then maximum growth rate you are declining. So obviously there will be a decline in the abundance, right? So it's declining, here also it's declining. And in between, there is this coexistence region where we have bistable equilibrium points. So now we are all set to discuss critical transition in the framework of a saddle node bifurcation, because these 2 points, they are saddle node bifurcation points. And it comes from this picture. You may not be always able to calculate those bifurcation curves analytically, but numerically it is obviously possible. Any question? Yes. He is having a tip here. Here, in this tip, here, there is a cusp point. So, or K may be. So it will be something like, I don't actually, it It will be like this. This point, okay. At this point, still there will be signature of critical slowing down. Fine. So if I am here, okay, I cannot see that eigenvalue is touching 0. Okay, but if I am there, it will not cross. So as it's stable, I don't remember the exact diagram, but I can still give you some idea. So let's say it is lambda, and I'm playing with my R, right? And this is lambda equals to 0. It has to be negative because this is stable. So it will be something like that. It will still touch this lambda 0 at the cusp point. You are just about to start your discontinuity is about to appear.
Use the mic if you can, because it will help those who are online. Thanks.
Hello. Yeah. So, so this cusp point, that that straight line that is connecting R and K. So this is basically when it is touching both the ends, like the maximum and the minimum. At that is the like the bifurcation. It's happening like from and connecting with this figure.
Which figure?
This one, this stable and unstable, where there are 3 equilibrium points.
There are 3 periods. So it is such as that point.
This, suppose we are both changing R and K, and we are in some sort of position where it's touching the
so that if you want to draw the bifurcation diagram that I have, this one, it is a codimension 1 bifurcation diagram, right? And if you want to vary both the parameters together, then this is my codimension 2 bifurcation diagram, right? So the point is that if you want to play both R and K together, you have to compare things in this figure, right? So this is a point where 2 saddle node bifurcation curves, they merge and disappear.
So like then that point is basically when the straight line touches both the extremals.
Yes. So that is the point where it touches here.
And below one also.
No, so below one will obviously be there.
Like this,
okay.
This
so
jump.
You mean to say yes. So you mean to say something is due to my figure. So I got your point. So this point, yes. Because then the bistability is about to appear.
Thank you.
Any other questions? So is it clear to everyone that, at one level, we're talking about equilibrium points and fixed points, right? But we also talk about, when we vary R and K, how do you reconcile this notion? Is that clear to everyone? Is there some, I hope it's clear to everyone, how can you have an equilibrium when R and K are varying? Is it clear to everyone what exactly is the intended meaning when we say, oh, in R and K are varying, but there is this equilibrium bifurcation diagram? Anyone who understands can maybe try to answer that question. I hope my question is clear. Is my question
I have
clear?
started from that question itself, right?
Right. It may be too obvious, but I just want to make sure everyone is clear about this. And there is no confusion on this very obvious point. Because because it's possible that we miss some obvious points along the way. The basic idea is that for any given set of parameter values in this model R and K, right, there is one or more equilibrium points, right? So, and depending on the initial condition, the system will reach one of those. Now, when he says, when we now vary R and K, the basic point there is that, we vary R, K. Let's take only one of them to make life. See, so very, very slowly. Okay, we vary that slowly enough that at every point in time, you are basically tracking the stable branch. Okay, so that's the sort of implicit assumption. If you now vary RRK very rapidly, that system has not even reached equilibrium, then you have in a very different domain altogether. Okay, R itself now becomes a dynamical variable. Okay, so in this framework, in the framework of bifurcation systems,
You're gradually varying.
we vary the parameters very slowly, such that it is much slower than the equilibrium time, the time scale that he mentioned, 1 over lambda, right? So, this varying in R and K is happening on a much longer time scale compared to that characteristic time scale. You had a question, somebody there in the back? Okay, thanks. Any other questions, points? If you, you can also make some comments or points if you have about anything we have studied so far. Because, this builds the foundation for rest of the week. So it's okay to stop a bit and ask any question and think about it. So basically what you have learned is, techniques of nonlinear dynamics, what is a fixed point, what is stability, and so on, right? That's one part of it. And second part of it is one classic model in ecology, which actually shows bistability, right? Bistability means, there are two fixed points, two stable equilibrium under a given environmental condition. Okay. And, if you think about it from a purely biological point of view, the fact that you can have very different outcomes for exactly same sort of environmental conditions seems a bit counterintuitive from a very if you are used to think from a very deterministic point of view. And what is also interesting in this is actually a deterministic model. There's nothing stochastic about this, right? But despite that, you can actually end up having very different outcomes entirely based on where you started off with. Okay.
So your initial condition will determine finally which state you are in.
And one useful thing to think about is that, what's the biology that can sort of maintain two very different types of outcomes under exactly same conditions? It's something, you should worthwhile thinking about. For example, in this, looking at, the equation, what are the processes that are undergoing that this equation represents? And how is it for the same value of R in that intermediate region? Depending on the initial condition, I could be in a very low population state. But if depending on some other initial condition, I could be in a very high population state. How can I explain this sort of, different outcomes entirely biologically? That's an useful exercise for all of you to think about and try to come up with some verbal justification. Okay. Yeah.
Very good question. Very good question. Very good question. I tried to address in the beginning. If there is bistability in the oscillatory state, okay, so yeah, so then this lambda that we have talked about, it was real valued, right? So then you have complex conjugates, right? And then the framework of critical slowing down, I think, will not work, because as much as I know, like so we have Professor R.I. Sujit who will be speaking here. He considers subcritical Hopf bifurcation. So in subcritical Hopf, what happens? There is a bistability between a steady state and an oscillatory state. Okay, so you have, so the diagram will look like this. So going like this, then there is a saddle node point, and there you have basically supercritical Hopf, and it is a limit cycle. Okay, So in this zone, you have a bistability of an oscillatory state and you have a steady state. So now, if I want to apply the question of forecasting, then the literature I have seen, people will always consider the time series from the lower steady state, and they will talk about when I am in the lower steady state, can I forecast? I'm going to switch to an alternate state, right? Because here, obviously, it's a saddle node point. I have not seen literature where people are just trying to track in the other way around. But there is a paper. I know that paper. It's in scientific reports. It's written by Tamastel. They talk about some other measures. So when you have bistability in oscillations, then how can you forecast it? But this critical slowing down based indicators probably, as much as I know, will not work. Obviously, there can be a new reaction of work. Because in real data, to find this, the absolute steady state, if fluctuation is bit more, I will in my next talk I'll come there. In the deterministic setup, let's say you have a steady state. Now, when you add noise, then that steady state can start oscillating. So Team Coulson and Pageman Rohini, they have a fantastic paper on that. And so the important is that in the presence of noise, the qualitative nature changes, right? And those who are working with real data, they see that there are oscillations present in their data, right? Now, using those oscillatory data, can they forecast? They are about to switch to an alternative steady state. So that is, but to me, it's an open question.
Am I audible? So I have some question about the terminology. You started with the subcritical Hopf. So while changing the parameter,
I have started with a supercritical Hopf.
yeah, sir. Yeah. And then subcritical.
The subcritical Hopf I did not discuss, but so this is one form. Okay, it is one form of subcritical Hopf, but there is also another form of subcritical Hopf where from a steady state you switch from an unstable state you switch to an unstable limit cycle attractor, and there is a steady state in between. That I did not discuss here. So it will be like this. So you start from an unstable one, it becomes stable, and here you have an unstable limit cycle. The point is that the limit cycle itself is a closed invariant curve, right? So if you are on to that closed invariant curve, you are there forever, right? But here it is an unstable. So if you give a tiny perturbation, you're going to go away from it, right? So this is, in a classical sense, subcritical Hopf. And
so all these transitions, they are called critical transitions?
No, obviously not. So Bishu already mentioned that in general, when there is a sudden change in the nature of an equilibrium point, we call it a critical transition.
Okay, so depending on the bifurcation, we can classify this critical transition?
And you can, exactly. So that's why I started with catastrophic and non-catastrophic. Okay. So in general, this the system that involves catastrophic bifurcation, like saddle node bifurcation, you can put it in the framework of critical transition. Okay, but if it is non-catastrophic, then if it is not saddle node, then they are under this non-catastrophic.
Question.
Yeah.
So in that subcritical Hopf bifurcation thing, so initially the system is on the stable fixed point, and then it is approaching, like it is going to lose the stability of that fixed point. So why do you think the critical slowing down won't be observed there?
No, so I don't see, I am not telling here, it will not be observed, right? If you come from that part, you will be having a real part and also as well as the imaginary part, right?
For the limit cycle.
For the limit cycle.
Yes.
But here, if you are on the lower branch, obviously critical slowing down will be observed.
Okay, so then can you clarify what you told?
I told that if you want to forecast that a system is switching from the steady state to an oscillatory state, Normally, we consider this lower one because we want to see, can I forecast that the system is changing from the steady state to from an equilibrium steady state to a non-equilibrium one, or from an absolute steady state to an oscillatory one.
Yes.
Right? But if I want to ask the other way around question,
Okay.
the other way around question normally we do not ask.
Okay, I understand.